Hello everyone, welcome to the Artificial channel. At this time, we will learn about multiply linear regression analysis. First of all, do you know what is multiply regression? Multiply regression is a regression or prediction model that involves more than one independent variable or predictor. Like other statistical analysis tests, in this multiply regression test, there are also many types, methods, and even data processing applications that we can use. The difference between the various types lies in the scale of the data per variable. Watch this video to find out the types of multiply regression one by one. First is multiply logistic regression. This regression model uses dichotomous data as the dependent variable. The dichotomy has a categorical form where the number of categories is 2 categories. An example case is boy and girl. Good or bad? Yes or no? That is an example for the dependent variable. While for the independent variable, it also uses a dichotomous variable, but is not required. You can use variables in interval, radio, ordinal to multinomial data scales. The example for this multiply regression model is the effect of smoking and gender on the incidence of lung cancer. Here, smoking has a yes or no category, while gender has a male or female category. For lung cancer incidence, itself has a yes or no category. Two methods that are often used in multiply regression are the logit and probit methods. Second is multiply ordinal regression. In this type of regression, the dependent variable used is data with an ordinal scale. An example of an ordinal scale is champion. It can be first, second, or third place. Meanwhile, the independent variables can also use ordinal data or other forms such as quantitative or qualitative. This type of regression has its own uniqueness, namely the independent variable. If using categorical data or qualitative data, it is called a vector. Then, if the independent variable use numerical or quantitative data, it is called covariates. There are 5 calculation methods for ordinal regression types that you can learn yourself through various media. The example of multiply ordinal regression is effect of income level and age on IT knowledge level. In this example, income level is a factor that has categories of low, medium, and high, while age here is a covariates where the scale data used is numerical data. Furthermore, the level of knowledge is the dependent variable that uses a data scale in the form of ordinal data. The categories for the level of knowledge are good, sufficient, and also less. The third is multinomial regression. Multinomial regression is a type of regression that uses the dependent variable in the form of nominal data that has 2 or more categories, while the independent variable can be more than one variable. This type is a type of regression that is almost similar to multiply logistic regression. The difference from this regression is that the dependent variable has 2 or more categories, while the multiply logistic regression only has category 2 or dichotomy. This regression actually also has similarities with ordinal regression. The difference is that the scale of the data in this regression is not graded or not ordinal. There is no better or worse statement. An example case for this regression is the influence of parental education and parental income on the choice of college major. In this case, parents' education and income are ordinal data scales, while choice of college major is a nominal data scale variable with more than two categories, such as first try, healthy, engineering, and others major. Fourth is multiply panel data regression. Actually, in addition to the various types of regression before, there are still many other types of regression, which are the development of the types of regression before. The development is in the form of complexity in the form of the time series data or time series and panel data. One of them is panel data regression, or often also referred to as a concurrent or cut regression. Panel data regression is a regression that predicts or models data whose time span is panel data, something that is followed continuously over time. For example, data for 2016, 2017 up to 5 years after. In linear regression of panel data, there is what is called multiply panel data linear regression. This happens if there is more than one independent variable in the regression. And lastly, which is also our topic at this time, is multiply linear regression. Multiply linear regression is a multiply regression model in which the dependent and independent variables have interval or radio data scales, quantitative or numerical. However, there is also a linear regression that uses ordinal data in the independent variables. The regression is known as multiply linear regression with dummy data variables. Remember, the dummy data lies in the independent variable, not in the dependent variable. An example for this case regression is effect of weight and amount of sugar consumption on blood sugar. Like other parametric tests, linear regression also has classical conditions or assumptions that must be met, so that the resulting prediction model will be blue, or best linear unbiased estimation. Classical assumptions on multiply linear regression include: first, data interval or radio. This assumption does not need to be tested. You just need to make sure that the data used is interval or radio data, numeric or quantitative. Second, linearity. The linearity assumption is tested by regression linearity test, for example, with an estimation curve. Third, residual normality. Residual is the difference between Y and Y prediction. Fourth, non-outlier. Outliers is data whose values are extreme or different from the others. Fifth, homoscedasticity is a condition where the variance of the error is constant or fixed. Sixth, non-multicollinearity is a condition where there is a strong intercorrelation or correlation between independent variables in the model. And the last, non-autocorrelation. Autocorrelation can be interpreted that there is a correlation between time. Now, I will give a tutorial on analyzing multiply linear regression using SPSS software. Step 1. Write name and table. Step 2. Change decimal to 0. Step 3. Change measure to scale. Step 4. Go to the data view. Step 5. Paste the data that you want to analyze. Step 6. Click Analyze. Then click Regression. Then click Linear. Step 7. Input variable Y to dependent. Step 8. Input x1 and x2 to independent. And then click OK. Here is the output. This is how we read multinomial regression output on SPSS. The first output that appears is in the form of a table of variables entered or removed. This table gives us information that there is only one regression model generated. The variables entire column provides information about what variables are included in the regression model, manage something, and school. The variables removed column tell us about the variables being removed or moved. The removal of a variable could be due to a problem in the data processing process. It could be because the classical assumption test or problematic data variants were not met. In this output, the removed variable column is empty because there are no discrete variables. Then this method column shows the method used in the data processing, namely enter. Then we move on the next output, model summary. Here we can obtain information about the magnitude of the influence of all independent variables on the dependent variable. The influence is symbolized by R or calculation, as can be seen in the model summary table. The value in column R is 0.999, meaning that the effect of the variable manage something, and school quality is 99.9%. However, this value can be said to be contaminated by various confounding values that may cause errors. Measurement for that SPSS provides an alternative value of R squared as a comparison of the accuracy of its effect. It can be seen that the R squared value is 0.998, which means 9.98%. This value is smaller than the R value due to adjustment. However, it should be noted that this value is not necessarily smaller than R, but it also sometimes larger. For more accurate prediction of influence, we can also rely on the adjusted R squared value, namely the R squared value that has been more adjusted and usually the most accurate. It can be seen that the adjusted R squared value is 0.998 or 9.98% of the influence of the independent variable on the dependent variable. The next column is model summary. Table shows the level of accuracy of the regression model, which can be seen in the standard error of the estimated column. The value is closer to 0, the more accurate it is. With a number of that size, it can be said that the model format is accurate. Next, we turn to the ANOVA table. The ANOVA table shows information about the effect of the independent variable on the dependent variable simultaneously. In this table, there are several things that don't need to be discussed. First, sum of square, and second, mean square, because we don't need them to conclude whether or not the independent variable influences the dependent variable simultaneously. To make that decision, first, look at the value of sig. In the ANOVA table, the value of sig listed at 0.00. We can easily conclude that the variables of manage something and school have a joint effect on audit quality. This is by following the sig level 0.05 as the cutoff value from the significant value. This means that if the probability value significant is below than 0.05, then all independent variables affect the dependent variable and vice versa. After reading the ANOVA table, we continue reading the coefficient table. This table is useful for seeing the effect of the variable partially or individually. The output can be seen below. In the coefficient table, represent various important and unimportant information. The important information consists of variable names, constant value, t-values, and significant values. The information that is not important is the standard error and the beta value in the standardized coefficient column. It is not important because the standard error here is the standard error per variable. We don't need that because we only care about the standard error estimate. I took the data from the BPS. Maybe that's all for this video. Thank you for watching. Don't forget to like, comment, share, and subscribe. See you!